Hello, welcome to CE 3305, Engineering Fluid Mechanics. This is the second part of Lesson 1. And in this part, we're going to look at a particular problem in the textbook that will give us a chance to convert units. So we'll deal with what your textbook refers to as the grid method for unit conversions, as well as dealing with units in different measurement systems, and we'll also get to study the ideal gas law. So let's first take a look at the ideal gas law. So the ideal gas law is a category of laws called an equation of state. And what the equation of state does is it gives us a way to describe the state of the gas under any conditions of pressure, temperature, volume, and then total molecular weight. The version of ideal gas law I learned back in chemistry was PV equals nRT. Another version is shown here, PV equals MRT, and then probably a preferred one from my personal use would be pressure times volume equals M over cap M RT, where little m is the mass of the gas and big N is the molecular weight. They're all equivalent. Probably the hardest thing is to remember what the ideal gas constant is, and then also be sure that the units are considered correctly. The ideal gas law is pretty useful for gases. It is not exactly perfect in the sense that the real gases don't necessarily follow it, but they do at the kinds of temperatures and pressures that we commonly deal with. So as long as we're not dealing with gases inside an explosive situation or at solar temperatures and pressures, we're pretty close to the ideal gas laws. Okay, the problem I want to examine rapidly is this one, example 1-2, and we're asked to find the total weight of a 17 cubic foot tank of nitrogen if the nitrogen's at 500 psi absolute, and the tank itself weighs 50 pounds and the temperature is 20 degrees Celsius, and we're told to work in SI units. Now I like this as an example because it's mixing units and it's going to require unit conversions and a little bit of thinking. So this is a good place to start. The other thing to get out of this lesson is a format or a structure for presenting your work for when you're uploading your homeworks. So let's begin. So what you'll want to do is you'll want to identify the class and probably your name up here. So I will be called solution. And then the page count. And just start with one of. And I have no idea how many pages this will take, although at the end I can back count and recover the total count. So start off with a problem statement. And here we restate the problem. Find total weight of a 17-foot cubed tank of nitrogen at 500 pounds per square inch absolute. Vessel itself weighs 50 pounds force. Temperature is 20 degrees Celsius. Okay, so there's a problem statement. I recommend a sketch. Plays the same role as a free body diagram does in other mechanics, but mostly the sketch helps you organize your thinking. So here I have a tank. I know that the volume is 17 feet cubed. Temperature is 20 degrees Celsius. and the internal pressure is 500 pounds per square inch absolute. Let me list what I know. So my known values are the volume of the gas, pressure, temperature, and the weight of the tank. We'll go ahead and substitute or supply the numerical values, although some of these are pretty repetitive. Okay, so problem statement sketch known. Let's list the unknowns. We want the weight total, which equals weight gas plus weight of tank. We know the weight of tank, so our real unknown is the weight of the gas. Governing equations. Try to get in the habit of writing this up front, although as you're working through problems, you sometimes will have to determine a governing equation as you go. In this case, it's the ideal gas law. Pressure times volume equals M over cap M RT. Problem statement, sketch, known, find, in your governing equations. We're ready to work to our next page. And now we start our solution. Well, what do we know? We know that the weight of the gas is equal to mass of the gas times the acceleration of gravity. Mass of the gas, we can get that from the ideal gas law by rearranging it as pressure times volume times molecular weight divided by R times T. R is 0.0821 liter atmospheres per Kelvin mole. That's one of many ways to represent it. It's the one I remember. And now we have to figure out the mass of nitrogen 2. Well, the mass of one nitrogen molecule is 14.007 grams per mole, but there's two of them. So the nitrogen gas, diatomic nitrogen, is 28.014 grams per mole. Basically, every mole is producing 28 grams. And where I found that out from was a periodic table of elements. We have nitrogen. Monatomic is 14.01 grams per mole. Diatomic, which is how nitrogen gas would exist in a tank, is 28 grams per mole. And if you don't have your own table, it's right here. Just Google search and you find it. All right, and returning to our documentary steps. So we're going to need volume in liters and temperature in Kelvin and pressure in atmospheres. So for no particular order, let's start with the volume. Volume is equal to 17 feet cubed. And now I have to recall that there's 1 meter for every 3.28 feet, I'm going approximate here. 1 meter, 3.28 feet. 1 meter, 3.28 feet. And there are 1,000 liters in 1 meter cubed. So 17 cubic feet, and we have the meter to foot, meter to foot, meter to foot to keep cubics into cubics. And then we know there's 1,000 liters in a cubic meter. And if we perform the arithmetic, we get 481.76 liters. That's the volume. Next thing, degrees Kelvin is equal to degrees Celsius plus 273. We looked that up in our chemistry book. And so we now know that the temperature in this case is 20 degrees plus 273 equals 293 degrees Kelvin. So that's the temperature. Temperature, volume. See, last thing we need is the pressure. Pressure is 500 pounds per square inch absolute. And you would have to know or memorize or look up that there's 14.7 pounds per square inch absolute in every 1 atmosphere at standard temperature, which is 34.01 atmospheres. So now we have the pressure. Now we can solve for the mass of gas. Mass of gas is 34.01 atmospheres. Volume is 481.76 liters. Molecular mass is 28.014 grams per mole. That's all divided by 0.0821 liter atmosphere per Kelvin mole and 293 degrees Kelvin. Let's be sure that all that cancels out. Liters in the bottom, liters in the top, gone. Atmospheres in the top, atmospheres in the bottom, gone. Kelvin down here, Kelvin up here, gone. Moles, moles, the only thing that's going to be left is grams. And there's 19,000 of those little suckers. 19,071.5 grams of nitrogen gas. To my German students, in the US, we use the decimal point as the delimiter for fractions, and we use the comma as the delimiter for thousands and 10,000s. I believe it's the complete opposite for y'all. There's no way I'll successfully change, so just be aware of that. All right, so now we know the mass of the gas. The next thing is to find its weight. Well, the weight of the gas is simply that 19,071.5 grams. 1,000 grams makes a kilogram. 9.81 meters per second squared will give us weights in newtons. 187.09 newtons is the weight of the gas. Now we need to convert the vessel weight to newtons. We know that the weight of the tank is 50 pounds force. There's roughly 2.2 pounds force for 1 kilogram mass at standard acceleration, times 9.8 meters per second squared is 222.72 newtons is the weight of the tank. Total weight. Sum those two up. Weight total equals weight gas plus weight tank. 187.09 plus 222.72 equals 409.81 newtons. That's the total weight in newtons, and in theory we would be essentially done, but let's convert it back to pounds just for the heck of it. So 409.81 newtons is equal to 409.81 kilogram meters per second squared. 1 over 9.8 meters per second squared 2.2 pounds force 1 kilogram is 21.99 pounds. And last, we probably want to complete a discussion. We need the intermediate values. Especially R and the molecular weight of nitrogen gas. We needed to recognize that it was diatomic. We need a periodic table of the elements. And the final answer here has far too many significant digits. More likely useful answer with regard to significant figures would be 410 newtons or 92 pounds force. Remember in your answers, the units are part of the answer. Okay, and in fact, I made a there. And that's a good example that illustrates the unit conversion. Now this 1 kilogram per 2.2 pounds force, I mean, I've done this a while, so I have that committed to memory. But if I didn't, I can go look that up on the internet and find the unit conversion values. This is a preferable way to go into the internet and finding something that says to get pounds into newtons multiply by, and there'll be some number. That's very unreliable because you always get the numbers upside down. Okay, that should pretty much conclude the first lesson. Let's review what we learned with regards to our first lesson. We learned the definition of a fluid. We looked at stress-strain diagrams in a conceptual sense. We learned representative elementary volume. We learned dimensions in units and the ideal gas law. And that should be a